Okay, so students, hello and welcome to this session in our series of revision of vectors and calculus. So this is session number 3 for this revision series for class 11 physics. And in this session we are again covering the basics of application of vector algebra and calculus for the subject of physics. So once again, if you have not been part of this series earlier, then I urge you to please go through the session number 1 and 2, where we reviewed the early part of vectors, better understand this series. Okay. So far in our review of vectors, we have understood about representation of vectors and basic vector operations like multiplication of a vector by a scalar and vector addition and vector subtraction, both by the component algebra method as well as the geometrical representation of vectors. So in this session, we will start with the product operation of vectors. So we will start with the first type of product operation, which is called the scalar product or the dot product. So once again, since these are revision lectures, so I will be focusing more on the application of dot products or application of all these concepts in physics rather than on the basic derivations, etc. So if you need to go through the basics more carefully, then again I would ask you to refer to any standard reference book or a more basic set of lecture series. This is more for a revision for students of class 12th, the revision of the class 11th portion of physics. So let's start with scalar product. Okay, or also known as the dot product concept of two vectors. Okay. So this is an operation that is applied to two vectors. It operates on two vectors, and this is the symbol for the operation. So as you know, this is read as the dot product of vectors A and B. And the definition or the simple formula that gives us the value of the dot product is product of magnitudes into the cosine of theta, where theta is the angle between the two vectors. So this is the formula or the definition, where E is nothing but magnitude of the vector A. Capital B symbol here is magnitude of the vector B, and theta is the angle between the vectors A and B. So let's discuss some of the important properties and features of this particular vector operation. So first of all, we can see that dot product is an operation that applies to two vectors. On two vector quantities. Okay. The output of this operation is a scalar quantity. So on operating this, it gives us a scalar quantity. That scalar is AB cos theta, okay, which can be positive if theta is acute, that is theta is less than 90 degrees, can be 0 if theta is equal to 90 degrees. On the other hand, it can also be negative if theta is obtuse. that is theta is greater than 90, less than equal to 180 degrees. Okay. So this is the basic definition and the essential properties of dot product. Now next, let us look at the interpretation of dot product. So the geometrical interpretation. So in geometrical interpretation, we'll understand that supposing we have two vectors A and B whose geometrical representation is like this. Okay. So let's say this is the vector A, and this is a vector B. Such that the angle between them is theta. Okay. Now we know that by definition, we just saw that A dot B is equal to AB cos theta. Now in this diagram, you can see that if we drop a perpendicular from B's head onto A, if we drop this perpendicular here, okay, then this quantity, which is basically what we call the projection of the vector B along the vector A, okay, this projection by the trigonometry of this triangle is nothing but B cos theta, because this is B in magnitude. So you can see that this is equal to, that is the magnitude of the vector A. So it is the product of A's magnitude with vector B's projection on A. Okay. So this quantity here, this you can see is the projection of vector B on vector A. Okay. Or inversely, we can also say it is a projection of A on B. Okay. So you can see that since A dot B is the same thing as B dot A, so we can also say that therefore A dot B is also the magnitude of B, okay, multiplied by the projection of A along B. In other words, we can also write it as B into A cos theta. Okay. So A cos theta here would be the projection of A on B. So this is the geometrical interpretation. Okay. And because of this geometrical interpretation, we can see that as far as physics is concerned, the most important application comes when we look at the work done by a force F. Okay. Let's assume it's a constant force through a displacement of S. So this quantity itself is defined as the product of magnitude of the force with the projection of the displacement along the force. So the basic definition of work done becomes like this, as you know. And you know that in terms of units, if force is expressed in newtons and displacement is expressed in meters, then work done becomes expressed in joules, or work done is calculated in joules, where 1 joule is equal to 1 Newton meter. Okay, so next we will look at a couple of examples where we learn the calculation of this dot product in context of work done by force, because that is the most important application of it in physics. So let's look at an example like this now. So we have an inclined plane, which let's say is inclined to the horizontal at 37 degrees. Okay. And we have a block of certain mass, which is sliding down from the position A, eventually to the position B. It is sliding down like this. So given that a block of mass m equal to 5 kilograms, okay, take the value of acceleration due to gravity as 10 meters per second square, slides down a rough inclined plane from A to B, okay, through a displacement of magnitude, say 20 meters. So this distance from here to here, let's say this distance is equal to, the magnitude of the displacement here is 20 meters from A to B. Also, the frictional force on the block is of magnitude, let's say 10 newtons. Okay, so we want to calculate the work done by each of the forces acting on the block. This is what we want to do in this application example. We want to calculate the work done by each of the forces that are acting on this block as it displaces from A to B. Okay, so you can just try out this question. You can pause the video and try out the question, and I will solve it for you next. Okay, so to solve this question, first of all, we will need to look at the force diagram, okay, or we will need to understand the forces which are acting on this particular body. So let's understand that first. So as you know, the gravitational force acting on it will be a force that acts vertically downwards. Okay. And the magnitude of that gravitational force in this case will become 50 newtons, because the mass of the block we saw earlier was 5 kilograms, and we have taken G to be 10 meters per second square. Also, we know that the angle of inclination is 37 degrees like this. Okay. Now, the other force which is acting on it, one of the other forces, is what we call the normal reaction force or the contact force, which will act in the direction perpendicular to the inclined plane. This is the force that the inclined surface applies on the body. It acts along this direction, which is perpendicular or normal to the inclined plane. So N is what we call the normal reaction force. And of course, we know that mg is the weight of the body or the gravitational force. Okay. And in this particular case, there's also the third force of friction which is acting. And that has been given to us as part of the problem as, so the body is going to slide down the inclined plane. So friction will always act in the direction that is against the slipping or opposite to the direction of motion. So this will be the frictional force. And this is also given to us as 10 newtons. So these are the three forces. So now next thing is we want to calculate work done by each of these. Okay. For the displacement from A to B, which we saw is of magnitude 20 meters. So in all of this, we can see that the displacement vector will be in this direction and it will have a magnitude of 20 meters. This is the direction of the displacement from A to B, let's say, okay, and its magnitude is 20 meters. Okay. So now to calculate work done by each of these forces, I need to calculate the angles. Okay. So this is where this diagram becomes important now. So if we extend this line and also extend the line along which the gravitational force is acting, which is the vertically downward line, this line over here. So if we extend these two lines, you'll see we can construct this right angle triangle here. So now we can understand that this angle here, okay, will be the complement of this angle. So it will be 53 degrees. Okay. So for the first thing, we want to calculate the work done by mg. So that will be the dot product of gravitational force with respect to displacement. So that should be the product of the magnitudes, that is mg into s, into cosine of the angle between the two. You can see that the gravitational force is at 53 degrees with respect to the displacement vector. Right, so this will just become 50 multiplied by 20 multiplied by cos of 53, which is 3 by 5. So we can see that this will be positive of 600 joules because we have taken this in newtons and meters. Okay. So that is the first of the three forces, the work done by the first of the three forces. Now, we have not calculated the value of normal reaction in this case. I'm sure all of you can calculate it, okay, from the vector diagram. But you will see that for the calculation of work done, it is not required. Why? Because the normal reaction is actually perpendicular to the displacement. So the second of the three forces, when we come to that, this was work done by the gravitational force. When we come to the second of this, the work done by normal reaction, we can see that the dot product here will result in 0 because the normal reaction is perpendicular to the displacement. So the work done will become this, and we know that cos 90 degrees is 0. So the work done by normal reaction turns out to be 0. So far these are two of the three answers that we've got for calculation of work done. Gravity is doing positive work of 600 joules. Normal reaction is doing 0 work in this case. Okay. So just take a look at the diagram once more and make sure you understand these two results. And then let's come to the work done by friction. Now in the case of friction, you can see that the direction of friction is exactly opposite to the direction of displacement. So the angle between them is 180 degrees, or their directions are diametrically opposite. So the work done will come out to be a negative quantity, and let's see how much it is calculated to be. So this quantity now, work done by friction, so we calculate the dot product of friction and displacement. So as you saw in that diagram, that friction was the force that was acting in the direction up the inclined plane, whereas the displacement of the block was happening in the direction opposite to that. It was happening in the direction down the inclined plane. So the angle between them 180 degrees. Okay, so this will become, because the frictional force points opposite to displacement. Okay. So you can understand here that this will become minus of Fs. So the work done by friction will become negative of 10 newtons multiplied with 20 meters. So friction will do a work of negative 200 joules, which we've already discussed earlier, that when a force acts at an obtuse angle with respect to the displacement, then the work done by the force is a negative quantity. Or when we take the dot product of two vectors which are at an obtuse angle, then the dot product results in a negative scalar quantity. So work done, as you know, is a scalar quantity, and you can see that in this case, one of the forces is doing positive work, the other is doing 0 work because it's perpendicular to the displacement, and the third is doing negative work because it acts at an obtuse angle. So this simple example illustrates the application of dot product in context of work done. Okay. Now next we move on to understanding dot product in unit vector notations. So scalar or dot product in component form. Component notation. So this is given by a very simple formula that if in general the vector A is having rectangular or three-dimensional components AX, AY, and AZ, and the vector B similarly having components Bx, By, and Bz, then the dot product is given by this simple relation. So this particular formula, as you know, comes from very simple property of dot products. One is the distributive property. That is, if we take the dot product of A with the sum of two vectors, we can express it as A dot B plus A dot C. And also from the property that the dot product of any unit vector with itself is equal to unity or 1, whereas the dot product of any unit vector with a perpendicular unit vector will result in 0. So when we use a combination of these properties in this, we get this particular formula. So as I said, I'm not focusing too much on the derivations and formulas since this is a revision lecture. We're focusing more on the application. So when we have two vectors in component form, this is how we can calculate the dot product. Okay. So let's look at a quick example. So suppose we have vector which, let's say, represents electric field given by 20 I cap minus 15 J cap. The unit of electric field you will learn at a later stage is newtons per coulomb. And a particle makes a displacement of, let's say, in meters. And we want to find out the potential difference across the displacement S. Given that the formula of potential difference is negative of E dot S. Okay, so this is again an application example I'm showing you. If you don't know this formula right now, don't worry about it. You will learn it in the chapter of electrostatics. So if we have a uniform electric field, so it's just a vector given by this relation, and that field is, and we are making a displacement of so much in this field, then the quantity called potential difference is defined as minus E dot S, or negative of the dot product. So how we'll calculate that now? Let's understand this. So the calculation of this potential difference here will come from this application. So it is negative of this vector 20 I cap minus 15 J cap, dot product with 3 I cap plus 6 J cap. So this is a two-dimensional example. So we will just reduce the above three-dimensional formula into two dimensions. The Z components are not there, they're 0. So first, just take the negative sign common. Now the product of the X components of the two vectors here will become 20 into 3. And the product of the Y components will become minus 15 into 6. So this will come out to be 60 minus 90. So with this minus sign, this quantity now comes out to be positive of 30. So this potential difference, as we can see from this formula, and then with this substitution of the values, the potential difference comes out to be so much. And later you will learn in electrostatics that the unit of this will become volts. 1 Newton per coulomb multiplied by 1 meter is defined as 1 volt. So this is an example of the application of dot product in something other than work done in the formula of potential difference in terms of electric field and displacement. So once again, if you're not familiar with the concept of electric field and potential, don't worry about where this formula came from. At this stage, just concentrate on the application of the dot product. Okay. So this is about scalar product or dot product. Okay. Now, one more thing we should understand before we move on to the next topic is that scalar product or dot product can give us a very useful method to calculate the angle between two vectors given in component form. Okay. So calculate the angle between any two vectors expressed in component notation. We can use the dot product formula that if A dot B is defined as AB cos theta, then theta becomes the cosine inverse of A dot B divided by AB. So for example, given one vector, which is let's say 20 I cap plus 20 root 3 j cap, another vector which is let's say 10 I cap minus 10 root 3 j cap. Now we want to find theta, the angle between vector A and B. Okay. So that's where we can make use of this formula above. We can make use of this. So you can see that in this particular case, A dot B again I've taken a two-dimensional example. So this will become 200 minus of 600 or negative of 400. Okay. Whereas magnitude of A okay. So that will become 40. Magnitude of B is 20. So you can see that cos theta is A dot B divided by magnitude of AB, or theta is cosine inverse of A dot B divided by AB. So just substitute the value of A dot B from here and magnitude of A and magnitude of B from here. So it becomes cos inverse of minus half. So now that we'll know means that theta is 120 degrees. This is from the fact that we know that cos 60 degrees is half. Therefore, cos 120 degrees is the same thing as cos of 180 minus 60, which is minus cos 60. It's minus half. Okay. So 120 degrees is cos inverse of minus half. So we are making use of this concept here. Okay, so just take a look at this and make sure you understand how we use this particular application of dot product here. Okay, now another interesting little fact and application of dot product is that we can see how we derive the formula for direction cosines of a three-dimensional vector using dot product. Okay. So We have talked about this earlier when we were looking at the component representation of vectors in 3 dimensions. We understood about the direction cosines of a vector with respect to the xyz axis. Of a 3-dimensional vector. So we have a vector with 3 components like this. We saw that cos alpha was given by this formula, cos beta by this, and cos gamma by this, where alpha, beta, and gamma are the angles made by the vector with respect to the positive x, y, and z axis respectively. So this concept we've seen earlier. Now let's see how we can use dot product to prove this or to derive this. Okay. So the vector A is dot product with I cap, okay, is equal to x, and this should be equal to magnitude of vector A multiplied by cos alpha, okay, because as you can see, A dot B is equal to AB cos theta. So if you take the value of the second vector as I cap, okay, then its magnitude is 1 and theta is nothing but alpha. It is the angle of vector A with respect to I cap, which is the x-axis. This is along the x-axis. Okay. So that's how you can see you get this. Okay. So now you can see from this that cos alpha is ax upon a. And similarly, you can see that dot product of the vector A with j cap will give you ay, and by definition that is nothing but a cos beta. Dot product of the vector A with k cap will give you az, which is nothing but a cos gamma. So this shows you how the formula of the direction cosines come out to be what we've seen above here. So I told you when we were discussing about direction cosines that we would understand the derivation of the formula or where the justification of the formula at a later stage, and this is how you can do it very easily. Okay, so that is about scalar product or dot product. Now next thing we will look at is the cross product. Next type of operation we look at is cross product of two vectors, or also known as the vector product. So this is the representation of this operation, and it is given by this definition. So the left hand side, this is the vector product of two vectors A and B. On the right hand side, this gives us a vector quantity such that the magnitude is AB sine theta, where as usual A and B represents the magnitude of the vectors A and B, and theta is the angle between them. And along the direction of the unit vector n cap. Now this unit vector has a special significance. This unit vector is perpendicular to the plane of vectors A and B. Okay. So we'll discuss more about the direction of this unit vector, but let's first understand the definition. So the cross product results in a vector quantity whose magnitude is given by this relation, AB sine theta, and whose direction is given by this unit vector, n cap, which is the unit vector perpendicular to the plane of A and B. Okay. So incidentally, the magnitude of A cross B, which is AB sine theta, has a special geometrical significance. Let's look at this, the geometrical interpretation of this magnitude of the cross product. Then you can see that the quantity B sine theta is nothing but this perpendicular here. This perpendicular is B sine theta. So ultimately it's like this, that if we draw the parallelogram formed by A and B, if we use A and B as adjacent sides and we draw a parallelogram like this, then the area of this parallelogram, this total area, the area of the parallelogram formed by vectors A and B as adjacent sides, this area is equal to base multiplied by height. So that base is nothing but the magnitude of A, and the height is nothing but B sine theta. So this area equals to AB sine theta, which equals to the magnitude of A cross. So this is a special geometrical interpretation of the cross product, that the magnitude of the cross product equals to the area of the parallelogram formed by vectors A and B. Okay, next thing, let us understand how to determine the direction of n cap, the unit vector of A cross B. Now, this is something that often causes confusion for students, while at the same time it's very important in applications in physics. It's very easy to mix up the direction of n cap and ultimately come up with the direction opposite to the actual direction of n cap. So it's important to pay attention and understand this if you're not confident about it from before. So the direction of n cap, the unit vector of A cross B. How do we understand this direction geometrically? Let's get that. So this is determined by what is called the right hand palm or curl rule. So there are number of ways to understand this. Let me start by explaining the most simple method, that in my mind the most simplest method. Okay. So that is something like this, that if we are calculating A cross B and geometrically the two vectors A and B are like this. So if this is A and this is B, or in another example, suppose this is vector C and this is vector D. This is the angle between them. In this case, we want to determine the direction for n cap, the unit vector of E cross B. So now pay close attention here. So for E cross B, what we'll do is we will rotate A towards B. So for E cross B, rotate A to B. Okay. So in this case, the rotation will be in this sense. Okay. For C cross D, here we want to determine n cap as the unit vector in this example of the operation C cross D. So for C cross D, okay, rotate C towards D. So that would be this sort of a rotation here. I mean, you can always rotate it the other way also, but the smaller angle is this one. So it would be this sort of rotation. Okay. So now the thing is, if the sense of rotation is anti-clockwise, okay, as in this case, anti-clockwise is like this, then the unit vector n cap is the unit vector coming straight out of the plane. Okay. So it's coming straight outwards towards you. So n cap would be shown with a dot as the tip of the unit vector which is coming out. It is coming straight out. Whereas if the sense of rotation is clockwise, like in the above example for C cross D, okay, then n cap is going straight into the plane. Okay. So in this case, we would show n cap with a cross like this because it is going into the plane. So you're seeing the back of the arrow. Okay. So let me illustrate this with sort of three-dimensional diagram also. So suppose this is like a tabletop or a two-dimensional plane. This represents a 2D plane in which my original two vectors, which I had taken earlier, A and B, are lying. So A is a vector like this. Now here, suppose I am doing the operation A cross B. Okay. So when I do the operation A cross B, okay, I will rotate A towards B. So that will be this sort of a rotation. Okay. So this results here in a anti-clockwise rotation when I see from top. Okay, so that will mean that n cap is coming straight out of the plane. Okay. So the direction of n cap here will now become this. This will be the direction of the unit vector n cap, which is cutting this whole plane perpendicularly. This is the line perpendicular to this two-dimensional plane. So this is what we mean by this one. Whereas if in the same situation, on the same two-dimensional plane, we had this as the vector A and this as the vector B, and we are doing the operation A cross B. So we would have rotated A towards B, and this time you would have seen it's a clockwise rotation. So that would have told me that n cap is going into the plane. So in this case, my n cap for A cross B will be pointing like this. It will be going perpendicularly into the plane. Pointing in this sort of direction. Okay, so this is the understanding of. Okay, so let's do an example to understand this better. So now in this example, we have, let's say, this xy plane. Now in this we have a couple of vectors given to us. So we have the vector E, which is 20 I cap, and the vector B, suppose, which is minus 10 I cap plus 10 J cap. Okay. And we want to find E cross B, and secondly the unit vector n cap for A cross B. Okay, that is it coming out of the plane or going into the plane. And similarly, we also want to find the unit vector for B cross A. Suppose instead of doing A cross B, we do B cross A. Okay. So again, is it going into the plane or coming out of the plane? So you can just take a minute to pause the video and try out this question yourself, and I will be showing you the solution next. Okay. So as a hint, what you can do is, obviously you need to find the angle between A and B. So you can do that geometrically, or you can also find the angle using the dot product method, which we discussed earlier. Since the vectors are given in component form, you can find the angle between A and B by using the dot product method also, and then use the definition of cross product to calculate the three parts. Okay, so let's understand this. So one is, we can just find the angle between the two vectors, as I was telling you, by using the method of the dot product notation. So we just pick out those vectors from there. So we want to find out this angle theta. So we can just make use of the fact that theta is cos inverse of A dot B divided by AB. That's one method. So you can see that A dot B here is 20 into minus 10 plus 0 into 10 AX BX plus AY BY. So it's minus 200. Magnitude of vector A is 20 and magnitude of vector B is 10 root 2. Right. So theta becomes cos inverse of minus 200 divided by 20 into 10 root 2. So that is cos inverse of minus 1 by root 2, which will make it 135 degrees. So I know that theta is 135. So once again, I'm using that obtuse angle concept over here, that I know that cos 45 degrees is 1 by root 2. Therefore, cos 135 degrees is cos of 180 minus 45. Minus cos 45. So that is minus 1 by root 2. That's how I know that 135 degrees is the cos inverse of 1 by root. So I know this. Okay. So we are making use of that and we are getting the angle. Now we come to the cross product. Okay, so for the cross product, so I've got the angle. I know the magnitudes of the two vectors, this and this. So now I know that the magnitude of the cross product will be AB sine theta. So that will be 20 multiplied by 10 root 2 into sine 135. So that will be 20 into 10 root 2 into 1 by root 2, which is 200. Okay, which you can also incidentally see is the area of the parallelogram formed by A and B. If you were to just calculate this total area of the parallelogram,